The first step is ask. This is where you ask what are the problems and what are the constraints. Then after that comes imagine. This is where you brainstorm an idea for what you want to build. Then after that is plan. This is where you formulate exactly what you're going to do. And then create, which is where you follow out your plan. And then improve, which is where you create solutions to your problems. This is the engineering design cycle.
First step of the engineering design cycle is to ask. For the collapsible bridge, we had to ask what our problems and constraints were. The bridge had to span 4 feet while being able to collapse in a 1 cubic foot box. In addition, it must be no more than 8 pounds and hold 60 pounds, and from a collapsed state be able to set up in a minute 30 seconds.
The second step of the engineering design cycle is to imagine. This involves brainstorming different ideas to implement into our plan. In order to create a plan that allows the greatest success, we turn to research to find the components of the most effective bridge's capability. Tension and compression are two forces that all bridges face, and when the load of a force becomes greater than the bridge's ability to hold it, it collapses. Our challenge was to find a design that distributed these forces while being able to be taken apart. That's how we turned on planning a truss bridge, which Eric will explain more about.
Alright, since our plan was to create a truss bridge, the bridge had to be divided up into triangles. We decided to make the bridge out of wood since wood is light and cheap. Since no piece could be greater than a foot long, we made each triangle to have a base of a foot and a height of 1 foot as well. The triangles are connected at the bottom and at the top by a piece of wood. First, we thought, how are we going to connect these pieces of wood? And our first thought was to have hinges. But the problem with hinges is that you can only do it on one side. You can't do it on the back side. So that would leave the other side very vulnerable and thus weak. Then we thought to have a bolt. And a bolt system would be able to connect the front side as well as the back side. This would keep both sides strong and connected.
The last portion of the engineering design cycle is to improve. While following our plan, we ran into several design challenges which we innovated new ways around. The first challenge we had was with the bolts that connected the 4 triangles together. There was too much a gap between the bolt and the part that held the bolt. This allowed the triangles to wiggle, making the bridge unsecure. When force was applied, the bolts would loosen and fall out of the holding position. To fix this problem, we realized that the bolts needed something to keep them in place. At first we attempted to tighten the bolt holder, but the bolt still was not snug. The next idea we had was to secure the triangles as a whole instead of just the bolts. To do this, we tried zip ties. The zip ties were allowed to keep the bolts together and were easy to set up. Thus, the zip ties were the solution to our problem.
The next design challenge had to do with the length and stability of our bridge. Since 4 triangles add up to exactly 4 feet, something had to be added to compensate for the extra length needed. Also, by using 1/3 pieces of wood, the width of the bridge provided no stability standing straight up. We decided to hit 2 birds with 1 stone by creating a T-shaped base that extended past the triangles. We used our minute and 30 seconds to screw in the base with our 2 screwdrivers. This created a time crunch but significantly increased stability and length.
For the FEDD results, our bridge did not place and it ended up holding only 25 pounds. This was disappointing because it wasn't our design that failed, it was the glue in the structure itself. Because the glue on one of these pieces over here was not able to set and it broke off. For advice for next year, if you're planning to use wood, start early and go often to the craft center because it'll take a lot of time to finish the project. The next advice we have is to build small prototypes, whether this is out of popsicle sticks or whatever. At least build it so we can first start getting an idea and test your design. On the final product, make sure that everything is exact and put together as professional as possible. And finally, don't be afraid to try new things and innovate your design.
The biggest takeaway from our project is the real-life applications of that design cycle. We could have easily given up when facing hardships, but we innovated new ways to accomplish our feats.
If we were to redo this project, first we searched out for better material. Wood is light and cheap, but it's not as strong as metal. Then we'd also search harder for an effective connecting piece that didn't jiggle as much as this bolt does.
In addition, we would have set more time for the whole project at the beginning of the semester to work at the craft center. Once we became familiar with what they had to offer, the project went by much more smoothly. This would have allowed for more prototype building and testing to be done.
In completion, all three of us learned valuable lessons that we can use to further our careers in engineering. With access to the Craft Center, Home Depot, and the library, we were able to formulate a plan that answered the challenge and revised it to perform up to our standards.
Thank you.